introduce our speaker. So hello everyone, welcome to the CAST seminar again. Just to remind you about question and answer. So there's a box where you can type questions in. Our speaker, Professor Eve Armstrong, may pause at points and ask for questions, at which point raising your hand, your virtual hand, there's a little emoji hand you can put up, and I will, or one of us will unmute you so you can ask your question. And you can also raise your hand throughout the talk, same procedure. Or if you want to wait till the end, you can put your question in the Q&A box or raise your hand at the end. Any of these things will work. So George, please go ahead and introduce
It's our pleasure today to have Eve Armstrong give this seminar. Eve, some of you may remember her, as she was a graduate student officially at UCSD and associated with CAST. Her PhD thesis was actually in observational astronomy and on basically the systematics of binary white dwarfs. And in fact, in her thesis, she made a discovery which is very important for multi-messenger astrophysics and gravitational wave physics in particular, because binary white dwarfs that are unresolved sources of gravitational waves are kind of a key interesting background. So there's a connection there with a lot of interesting astrophysics. And that, I'll say, is one of the hallmarks of Eve's work, is that she has extremely wide-ranging interests in physics. And so when she left UCSD, she became a postdoc and essentially took a new direction, looking in neurobiology and mathematical techniques in particular in data acquisition techniques, working in Henry Abarbanel's group in the biocircuits center. And so she was a postdoc here, and some of you may remember her from that time. Since then, she went and she was a postdoc again in that subject, in neurobiology and neurophysics, I should say, at UPenn. And now she is an assistant professor of physics at the New York Institute of Technology and a research associate in the Department of Astrophysics at the American Museum of Natural History. So take it away, Eve.
George, I'm humbled by that introduction. Thank you. You omitted all the nitty-gritty bad stuff. Sounded fantastic. Thank you. Thank you, everybody, for coming. I want to reiterate what Karen just said. Please interrupt me at any time with questions, especially in this Zoom environment. I really appreciate more of an interaction rather than talking at you for 40 minutes. And just a heads up, I have aimed for this talk to be about 40 minutes long, uninterrupted. Okay, just for those of you who are a bit zoomed out already today, I wanted to let you know. So I'd like to talk with you today about a procedure, an inference procedure for studying nonlinear neutrino flavor transformation that I started about 4 years ago with George's group here at CAS. And here's where we're going. I'm going to describe to you the problem, or the problem as we see it, and then the model. It's a dynamical physical toy model of neutrino flavor transformation in core collapse supernova. I'm going to explain to you how we're going to be exploring this model. It's an alternative to traditional numerical techniques, traditional techniques of the field that are used to attack these problems, and a recent result, what it means, implications, and our plans for the future. So here's the problem. Neutrino flavor transformation is a nonlinear problem, which makes it a beast for traditional computational tools, which are typically very large-scale numerical integration codes. The astrophysics of compact objects presents a vast range of environments where neutrino flavor transformation might be happening and might be important for nucleosynthesis and for interpreting a detected neutrino signal here on Earth. But producing self-consistent solutions has been vexing, that's George's word, vexing to say the least. Recently, in the past decade or so, semi-analytic models have shown that the flavor field may fall victim to instabilities which were hidden, artificially hidden earlier from initial simulations by the necessary adoption of symmetries and simplifications. And it can be very difficult to adapt these large-scale codes to a variety of conditions that might or might not be important for understanding the role of flavor transformation in these environments. And I want to emphasize the might not. These numerical codes can search a vast range of parameter space. It can be very computationally expensive and time intensive. And many regions of these parameter spaces might wind up being actually irrelevant to your problem. The solution might not exist there. So you can spend an enormous amount of time searching large regions by brute force. And what we sought to do was examine an alternative tool, which is inference, and I'll explain to you in a moment what that means. Machine learning is a term you might be more familiar with. It's a type of inference procedure. And it can offer a means to very efficiently probe a variety, a vast range of physical conditions and parameter regimes that might or might not turn out to be interesting, and thereby augment or guide these existing codes to promising areas of study. There, I will pause. Any questions so far about the point of all this? Okay, again, please stop me at any time. So here's our model. It's a very simple, we call it a toy model of neutrino flavor evolution. It's steady state, two flavor, that is the nu tau and nu mu flavors are stuck together in a nu x flavor because we're mostly interested in the nu e. So we have nu e, nu x model. Single angle forward scattering model only. And it's a toy model because there are two of these neutrinos emanating from the neutrino sphere, not say 10 to the 58. Two of them, monoenergetic neutrino beams of different energies. They're interacting with each other as they propagate outward from this theoretical surface called the neutrino sphere. This is the protoneutron star, out from there into a detector, say on Earth. They're interacting with each other and with a background of weakly charged particles. And their densities are diluting as some function of this position, this parameterization R. And again, it's a steady state. There's no time here yet. The model is written in terms of the polarization vectors of each neutrino. After decomposing the density matrices and the Hamiltonians into basis polyspin matrices, we get this expression for the polarization vectors dpx, dpy, dpz for each of the two neutrinos. So there are 6 total of these equations. And I've highlighted, so the vacuum term is here. I'm going to ignore that. The neutrino-neutrino coupling term is here. I'm going to ignore that. And I'm going to focus on this term in the middle, which I've highlighted in blue. This is the neutrino matter coupling potential. And we decided to focus on this term in particular for our inference study because the matter potential is very poorly constrained theoretically, and it could impose a signature, a strong signature upon a detection. So it would be nice to be able to explore what this thing actually looks like. So we're doing a parameter estimation where what we're doing is we know the model basically, but there are important parameters in this model that we decide to not know. And the parameters we decide to not know are governing this matter potential V of R. And I'll get to the specific form of that, the unknown parameters in a moment, but I'll just tell you for now that V of R, can you see the highlighting? If I scroll over, does the highlighting show up? Okay, great. Yes. V of R is going as a 1 over R cubed, and we have this coefficient Cm in the numerator, and that is going to be a parameter or parameters to be estimated in the procedure. This is a buildup to a much more realistic situation where first, we have more than 2 neutrinos, and second, we have a complicated structure inside the envelope. V of R represents multiple shocks, for example. So over the long term, as we add realism to the model, that's what we're aiming for. But right now, we're looking to see how inference works on a very simple system. Okay, this is a good time to pause again. Questions? At a certain point, I'm going to refuse to speak unless somebody interrupts me.
Manjit has a question.
That's what I do to my students.
Yeah, I'm still not entirely sure what inference is exactly. You said it's similar to machine learning, but
Yes.
I didn't fully get what that was.
Yes, thank you. Sorry, are you Sanjit?
Yes.
Name popped up. Okay, you do not understand yet because I have not told you yet.
Okay, thank you.
Thank you. Thank you. It's coming. I'm going to first describe to you the model and the goal of the estimation, and then I will explain to you how we're doing it.
Okay.
Thank you for the question.
Thank you.
Here's our specific scenario. So same deal. We've got I'm representing this differently now, but the neutrino sphere is here at a radius of 0. And then the detector, our Earth-based detector, is over here at a radius of 2. 2 is an arbitrarily chosen number. So at r equals 0, we're going to assume, and you can ask me later how well justified we are in assuming this, but I'm going to assume that the neutrinos are emitted in almost entirely flavor state E, mu E. Or to translate that into our polarization vector model, the Z component of the polarization vector P is 1, equals 1. Now, in the adiabatic limit, and what I mean by that is the neutrinos do not change energy as they propagate out from the neutrino sphere to our detector. So they maintain their energy, and beginning in a pure nu E state, you observe almost perfect flavor conversion, very efficient flavor conversion to the nu X state. So you're going from Pz equals 1 to Pz equals -1. In this region here, there's some region within the cloud where this happens. This is called the MSW resonance. And our question for the, so this is a established, well-established theoretical phenomenon. And our question is going to be, where in the cloud does that happen? So I want to be clear now, we are going to know within our inference framework, we are going to know where it happens. And we're going to challenge the inference procedure to correctly identify that location. This is a proof of concept that the inference procedure is going to be able to attack a problem that we don't know the answer to. We need a confidence check first. Okay. So the question is going to be, where does this happen? That is, specifically, if I have a detection here, and I don't have any other detections anywhere else, I can't cram my detector into the supernova envelope to make measurements deeper inside. Can I predict backwards that complete red line? Can I predict backwards that red, the full flavor transformation history? Or in other words, what measurements do I have to make? And, or what constraints on the physics must I place within the envelope to uniquely identify this location or this red trajectory here, simultaneously with that coefficient Cm governing the matter potential. Now, I didn't go into details of the model, but that coefficient determines the location of the MSW resonance, in part determines the location. So I want to estimate the value of Cm simultaneously with the shape of this red trajectory. Okay. I have not yet told you, just to be clear, I have not yet told you what in the world we're actually doing to do that, to accomplish this. So far, I have given you the quest that we have. So questions on the point here, what we're trying to do. Okay, let me check the time. Okay, I'm doing well on time. All right, here's how we're doing it. We're using an inverse formulation called statistical data assimilation. In general, I will describe an inference formulation as inferring from observations something of interest, such as a prediction of future observations. So machine learning, for example, you buy a new laptop and you go to Google and you type in G for the first time ever. This is your brand new laptop. And Google comes up with no ideas for you, so you have to type in the full word gummy bears You love gummy bears. You're going to buy gummy bears. Then you buy gummy bears 100 more times using the same laptop. Pretty soon, when you type a G into Google, Google is going to go gummy bears before you have to type in the entire thing. So this is a machine learning monster that learns your behavior and makes a prediction about your future behavior. The important difference between that and what we're doing. Okay, so machine learning falls under the umbrella of an inference procedure, but statistical data assimilation assumes that a physical model created the measurements. That's the difference. Very often in machine learning, you don't really care how the measurements were created. You just want to make a strong prediction about the future. Okay, so with data assimilation, we seek to optimally combine a model with data. And I'll show you in a few slides the mathematical formulation of what that sentence means. And importantly, in simulations, these are all simulations we're using now in the context of today's talk. I'm going to call it SDA because statistical data assimilation is just too painful to continue saying. It offers a systematic means to identify the measurements required to estimate unknown model parameters to a desired precision and to be able to make predictions to a desired accuracy. This little picture in the bottom right corner, I picked, I don't even know what that picture is from. So I picked it off Google because I thought it was a cute way to illustrate this slide. SDA was invented to predict the weather. Because in simulations, what you can do is you can invent whatever measurements you would like, even though technically they may not be measurable with current technology. So with weather prediction, you would do that. You would invent whatever types of measurements you would need. Measurements of the ocean at some depth in the ocean or something like that, something that nobody could actually do. And fiddle around until you get the estimate that you want. You get the desired precision you want, you get the prediction you want, and then say, okay guys, we need to invent this thing that can measure that. So this is how new instrumentation for weather prediction is created. More recently, it's been applied to biological neuronal networks, and that was my introduction to it. As George mentioned earlier, I was working with Henry Barbanel just a few years after he began applying this technique. He took it from the weather guys down at Scripps, actually, and he brought it to estimating parameters of biological neurons and neuronal networks. Now, in astrophysics, inference has, and please, anybody who's here who knows more about this than me, please tell me if I'm wrong. But I believe that inference is mainly used in a machine learning type of sense now within astrophysics, that is attacking big data, looking for patterns. Machine learning is a very powerful tool for pattern recognition. But more in recent years, just past 5 years or so, its utility for model completion has caught on in a few subfields of astrophysics. One is in the exoplanet community. It's called atmospheric retrieval, that's what it's called. They use observations of spectra of exoplanets in order to infer chemical composition of the atmosphere. They're looking for biomarkers. I don't really know much about that, but I know that that's almost a decade-old endeavor now. Alrighty, questions? No questions? I guess I need to try to be more confusing. Okay.
One question.
Yes. Yes.
Go ahead, Sanchit.
Maybe this will become clear as you describe the math behind this, but is this within astrophysics or just generally as a technique? How much data do we typically need to like do a good job at this technique? Because for instance, machine learning requires the bigger your training data set, the better your predictions, right? Is that also true for inversion?
That is a great question. Actually, that's what we're seeking to figure out in this study. We're asking how many constraints do we have to place on the neutrino flavor physics within the envelope to get our solution. But one answer to your question is it depends on whether you have a model. If you don't have a dynamical model that needs to be obeyed by your measurements, and I think that's the case for most the big powerful machine learning algorithms that are out there, don't necessarily have a model and so require much, much more data in order to get a strong prediction. To give you, let's see, give you a number. So in a machine learning, a classification scheme, I'm going to say you'd probably need in the thousands of sets of input-output pairs for your machine learning algorithm to begin to infer a pattern between your input and output, and then be able to infer, if you give a new input but no output, what that output would be. I'm gonna guess thousands to tens of thousands of pairs of data.
Okay.
But within our context, that your question is actually exactly what our question was.
Okay.
So great.
One other question. William Welsh, would you like to ask your question now or wait till later? It's in the Q&A box. I can unmute you if you would like. So raise your hand if you want to do now. Okay, well, we'll wait till the end then. All right, go ahead.
Okay, and now the Zoom bar is blocking the words. Okay, I can remember. So the task for the SDA procedure. Is there any way I can get, sorry, I can't read it. Together with the one Earth-based measurement. Okay, so we have one measurement that was taken on Earth, and that's the green dot over on the right. What constraints must we place on the physics to uniquely predict the flavor evolution within the envelope and estimate the coefficient Cm governing the matter potential? I said that already, but I wanted to put it back on the screen just to remind you. So this little figure here, I'm reminding you with the green dots where the quote unquote measurements are taken. We have a measurement at the detector, a pure nu X state of the detector. And then we're assuming, this isn't really a measurement, it's an assumption. Over at the neutrino sphere, we're assuming emission in the pure nu E state. Okay, so those are the locations of our two measurements. And this was the first experiment that we did. We published the first paper on this about 4 years ago. And we found multiple, I'm gonna call them degenerate solutions that did satisfy those boundary conditions. So they obeyed the requirements that we are emitted in the pure nu E state and we are detected in the pure nu X. But many of them look like this black line here, which, let me be clear, is a permitted solution given the information that we had given the procedure. Okay, so we gave it the information that we are evolving through the MSW resonance, like this curved red true state that you see. And we had given the measurements at the endpoints, but we hadn't given any other constraints on the physics within the envelope. And so many of our solutions looked like the black line, which were fine. But now, in this latest work, we wanted to go further and we wanted to ask, how do we break this degeneracy? How do we get every time, how do we get the procedure to get that red perfectly? So I'm sorry, I forget the name of the person who asked me the question just a moment ago. But this, I believe, is along the lines of what you were asking. How much data do you need to get a good prediction? That is our question. Okay. So now we're expanding the experiment, and there are 20 detailed here. Please don't, first direct your attention to the top rectangle here. Location of constraints on flavor of each neutrino, okay? So we first repeated experiment Roman numeral I, where we placed one constraint at the neutrino sphere in addition to our measurement at the detector. And we already knew that that was not going to be sufficient to break degeneracies. Then a second experiment we decided to try was, okay, let's say we place a constraint here within the envelope, right there at the center of the MSW resonance. So we tell the procedure where the center of the MSW resonance is. Is it going to be able to pick out, for example, the shallowness or steepness of the transition? Okay, how about if we say bracket the MSW transition? We give it the flavor at a rather arbitrarily chosen PZ of plus or minus 0.9. How about that? How about we give it the value of the flavor throughout the entire transition? This is starting to get a bit trivial, and this final experiment is utterly trivial, we give it the value of the flavor at every discretized location along the trajectory. So this final experiment 5 was just a check. You know, if it doesn't get this right, we're doing something really wrong here. So those were the 5 constraint designs, I'm going to say. And you can imagine, again, this is a very toy model, but imagine at a larger scale, more physically realistic model. Imagine there are any number of theoretical constraints you could place on the physics within the envelope in terms of the shapes of shocks, for example. Put those in and see whether they are consistent with the detection. Okay, so that's a much longer term plan, but that's where we're seeking to go with this toy set of experiments. Now, hang on, I'll stop for questions in a moment. For these five designs, we performed them twice. Once for a coefficient CM that's just a number, just one parameter to be estimated by the procedure. And again, where the coefficient is now varying as a quadratic itself. So the procedure knows about the quadratic form, but it needs to estimate the parameters L here, which designate how fast the fall off is, and eta, just the y-intercept. Okay. And again, this adding complexity to the coefficient is a buildup to adding a very complex structure of shocks within the envelope eventually. And finally, for these 10 experiments, we performed one search in a region of parameter space where we knew the solution existed. Okay? And what I mean by that is we performed the search in a region of parameter space that contained this the value of CM. And we performed the search again in a region of parameter space that we knew did not contain the solution, was completely irrelevant to our problem. The aim is to identify a litmus test. Can this inference procedure give us a litmus test for whether we're wasting our time? Because it doesn't take very long for the procedure to do this, and it would take a long time to rejigger these extremely complex codes to do one specific thing that turns out hundreds of thousands of computation hours later to have been irrelevant. Okay, so our hope here is that we have a simple litmus test that we can do real quickly and then guide a more complicated code to look at in more detail in a region that is relevant to the problem. Oh, that got cut off, but I already said it. Don't worry, you don't need to see more words than necessary. Okay, questions?
There are a couple of questions in the Q&A boxes on Zoom. So William Welsh, would you like to ask your questions?
It looks like he does. So you have to, I'll unmute you now, or allow you to talk so you can unmute when you're ready.
Hello?
Go ahead.
Okay, sorry, I can't tell if I'm muted or not, and so I'm talking to myself here. Okay, so sorry, these questions go back a bit, but the question was
sorry,
about...
should I go back to a previous slide?
No, that's fine. The big picture question was, is this sort of like a deconvolution type problem where you have you know the model, you have an input, and then output, but you kind of want to know the functional form or something like that?
Absolutely.
Oh,
Yes.
Okay.
Yes.
And so those techniques that work for deconvolutions would in some sense apply?
Oh boy, you know, I'm not an expert. Can you give me an example?
Anything where you have a transfer function. So you have a sharp
sure.
image, it goes through some optics and it comes out blurry. So you measure the blurry, you think you know what the optics are, and you want to know what the sharp image is.
Yes, so there are multiple ways to do that. So one way to do it, and it's the way we do it, we're extremizing a cost function. Is that along the, so imagine you've got let's say you have a least squares error where you've got a measurement and you've got a transfer function and then a variable representing that measurement, right?
Okay.
Or a variable of your model that represents the measurement. And in the very trivial case where the transfer function is 1, you are requiring that the difference between the measurement and the state variable of your model be 0, or be as close to 0 as possible, right?
Well, yeah, well, I'm thinking of it slightly differently, where you have your data and you think you have a model and you want to back propagate it to get your clean version. And in many of these cases, there are no like free parameters. Like
Yeah.
in a classic Fourier deconvolution, there's no free parameters. So you're not fitting parameters because all the information is there if you know the transfer function.
So you're saying that what you're seeking is the transfer function.
No, if you know the transfer function, what you're seeking is the input.
Sure. Sure. So you know the transfer function, you know the output.
Right, and you want to get the input, which is, and the output is a blurred version of the input.
Oh, okay. I see what you mean. Well, sure. I don't know a lot about what techniques the term deconvolution encompasses, but
Okay, well, we can take this offline. That's fine. I didn't mean to interrupt. But
no,
the other quick question.
Questions on interruption. You know what, William? Can we come back to this when I show you the form of the cost function that we're using?
Sure, absolutely.
Okay, all right. It just sounds very similar to me to what we're doing, but I think it'll help if we look at the mathematics of it.
Sunsheet has another question.
No, I just wanted to chime in on this a little bit. It sounds like from what William is saying, the problem is slightly more general in that we're trying to figure out what measurements would be useful to find a potential transfer function. So it's a step above like the problem we're posing here.
Right. Well, since you asked it, that brings me to the other question I had, which is if you do know the model and you're just trying to find out the parameters of the model, in some sense, can't you take derivatives, either analytic or numerical, to determine the sensitivity of your model to these parameters? And then that tells you which parameters are more important than the other ones.
But without measurements, what are you going to learn?
Well, you can learn that I should spend more time measure. Let's say you want to measure the energy output of a star, and you know it's more sensitive to temperature than radius. So if you can measure temperature more accurately than radius, you're better off doing that.
Mm-hmm. I'm not sure what to say because I'm not sure what are you trying to do?
Oh, earlier on, I thought you said one of the goals was to find out how, what I guess what data would be most informative for constraints. And I was thinking, can you kind of do this in the forward direction? Where
Well, here, you know what, this might help. We're not assuming that we know our model's correct. So in the cost function I'm going to show you, we do want to take into account the model. We want one term in the cost function requiring that we're obeying the model dynamics. On the other hand, we don't want our model to trump any data that might come along and inform us that actually our model needs some work. Okay,
right.
so
that's a really
in
good
our
point.
case, we want to we do want the model in there, but we want to be open to the possibility that the data are going to inform the model.
Got it. Yeah, okay, thank you. That helps a lot.
Okay, great, sure. And I'll show you that in a moment. And I actually, just to be kind to my audience, I didn't put in the nitty-gritty of the equations, but I can use my annotation thing to stick it on the screen if that'll help you. Okay, oh, here it is. Great. So we use an optimization formulation of inference where we're minimizing a cost function. Our cost function is called A0. I'll explain to you the A in a moment. Ignore the blue RF and RM for a moment. Just take a look at A model and A mesh. Let me start with A mesh. And this is what I mean when I say I did not explicitly write out what these terms are, and I can do that on the screen if you like. So A mesh is just your typical least squares error, assuming there's no transfer function between a measurement and the state variable that represents that measurement. So imagine your measurement is magnitude of a star, and in your model, there's no transfer function between the actual magnitude of the star and your state variable. Okay, so there's no noise in your instrument, for example. Okay, it's a one-to-one correspondence. Okay, so that's a least squares error term. A model imposes the model also. Okay, we're requiring the dynamics of the model that I showed you back maybe 8 slides or so ago. Okay. And there are unknowns, so there are some blanks in that model error term. And oh, finally, A unitarity, we want to impose the conservation neutrino number. But I want to focus on those first 2 terms because, have I written it down? Oh, RF and RM are relative weighting terms. I'll get to in a moment. Right, in minimizing both of these terms simultaneously, okay, we're minimizing A model and A measurement simultaneously. What we're doing is we're propagating information that is contained in the measurements over to the model error to complete unknowns of that model. Okay, so we're not giving the model complete weight. We're not saying this is our model, we're right. And these measurements, if they don't conform to the model, well, they must just be wrong measurements. No, we're saying, look, we think we know the model, but no, not quite. So there's a summation here over all measured states in this term, all measured states, which is a subset of all of the model state variables. Right? So the measurements of the measured states, and in our case, it's just the PZ components of the polarization vectors, not the X and the Y. Those measurements are going to inform the evolution of all of the state variables, both measured and unmeasured. So by measuring PZ alone, we want to infer not only the complete evolution of PZ, but also the complete evolution of PX and PY, all of the model components. So here, let me annotate. I really should have written that out for you because I'm getting so many interesting questions about what it looks like. I'm sorry, I'm using my finger. It's not going to look very pretty, but the measurement error is going to be Y minus H of X all squared, where say Y is your measurement. And X is the state variable of your model that corresponds to that measurement. And H is the transfer function. We take it to be 1 in this toy model. Okay, and then we're taking a sum over sub L and sub L, where L are all the measured state variables. Just a subset of the total, I'm going to say the total D state variables. So let me erase that and now write for you the model error term. I miss having a whiteboard right next to me. I miss seeing actual human beings. The model error term, so here's our model. It's X dot equals F of X, basically. F is, I mean, there are many a set of equations in this representation, all 6 of them. So my model error term looks like this, X dot minus F of X. Oh, comma P, I should say, all squared, where P are the unknown. The unknown parameters to be estimated. Okay, so it's in this way that information from the y, the measurements in the other term, is propagated over to here to estimate those p. And now we're summing, I'll just say over, I use d to represent the total number of variables of your model. All d, so L plus however many were not measured. That's what these two terms look like. William, does this have anything at all to do with what you were asking me? I thought this might help clarify.
Yeah. So if it were just a simple, least squares or maximum likelihood, there would be no a model term. Is that correct?
Yeah. Yes.
Got it. Yeah.
And
Exactly. That helps.
Right. So yes, thank you. So the main difference between what this SDA technique and a typical machine learning technique is, this guy is not there.
Great, thank you.
Sure, thank you. These questions really help me explain it better. Thank you. I take a lot for granted. Other questions about this? Oh, for anybody who knows about data assimilation, there are other methods. There's smoothing, filtering techniques you may have heard of. We are not doing that. We're using an optimization procedure specifically, which is the minimization of a cost function. Oh, and I should have stated in the beginning, one reason why we are using an optimization formulation is that it's integration blind. The cost function, the procedure that searches the state space of our model doesn't know about time, or sorry, I should say radius. And one problem with forward integration, which does know about radius, is that the neutrino trajectories from the neutrino sphere out to the detector, we're not just going like that, forward only. There's backscattering happening. And so it's more like a random walk sort of thing out to the detector, back and forth and up at weird angles, which is one reason why you can't use forward integration to put in the nonlinear neutrino flavor transformation into these models. So we're exploring optimization as an integration blind way of perhaps inferring those nonlinear trajectories. Okay. Does anybody else have a question? Okay. So the result, if I can get my cursor to work again. Oh dear. Oh, I just have to stop annotating. There, okay. Oh, we refer to the cost function as an action. That's why it's A0. It derives, you can derive our formulation of the cost function. You can derive it from the classical definition of the action of so a path and state space. On a path and state space, the true solution to your problem corresponds to the path of least action. That is, your model will take through its state space the path of least action. So I referred earlier to a litmus test that we're seeking. A litmus test that will tell us a priori, without having to look at the solutions themselves, that is, without having to look at the trajectories that the inference procedure comes up with, we'd like a very simple litmus test to tell us a priori whether a solution exists in the region we're looking. And what we're going to do is we're going to seek solutions that correspond to the path of least action, which you can calculate before you begin the procedure. Depending on what your model is, it's going to have a value corresponding to the floor of the action.
I think we had a question.
Oh, yes.
You want, let me allow someone to talk.
Yes.
Bahara, do you want to ask your question? Okay, maybe that's not working. Go ahead, sorry.
Let's see. Let me skip 2 slides. I'm going a little bit long. Oh, I can't. I can't do that. Okay, we have a problem. So it's not as simple as I've been leading you to believe. The cost function has more than one minimum because this is a nonlinear model. So up at the top, I've shown you a very idealized case where we have a cost function written in two variables, x1 and x2. They don't really mean anything. I'm just giving you this as a visual to help you understand what I'm trying to say. The case we're faced with is not this, but rather this. There are multiple minima on the surface of our cost function. How do we find the right one? How do we find the global minimum of our problem? It's a beast. So there are various ways to do this. We choose to do a type of annealing. You may have heard of this term, a simulated annealing. And here's what we do. Those RF and RM coefficients that I had in blue a moment ago, here's what they are. We use them as relative weighting terms for the measurement and model errors. Now the nonlinearity, the reason why there are multiple minima is the model term. The model is nonlinear. Well, let's get rid of it for a moment then. Okay, here's how we're going to get rid of it. We're going to start by estimating the cost using only the measurement error term, because that does have just one global minimum. I'll say that the surface of the cost function when we're dealing with only the measurement term is convex. The word that we use is convex, meaning shaped like this, if you can see my hands. There's one global minimum corresponding to the solution. Okay, well, that is useless ultimately because we want to know something about the model. So here's what we do. We call RM just a number. We're going to call RM 1. So RM is set to 1. And then RF. RF is going to be RF naught, some number RF naught times alpha to the beta. RF naught is some number very close to 0. It's not 0, but it's very close to 0. Alpha is some number between 1 and 2. And beta is what we call our annealing parameter. So here's what we do. We start by setting beta to 0. This is going to be an incremental procedure, an iterative procedure. We set beta equal to 0. And what we're doing now is we're saying the model error term technically exists, but it's very, very small compared to the measurement error, okay? So now we live in this very smooth cost function space where there's one solution. Let's find the minimum to that problem, okay? Let's find the minimum there and stay there for a moment. Crank up the weight of the model error slightly by an integer increase in beta. So what we're doing is we're very slightly imposing structure, model structure on the cost function surface. Starting again from where we estimated, we made our original estimate of the cost, calculate it again. We're going to get a slightly better solution, hopefully. Increase beta again, and repeat, and repeat, and repeat. And the idea is that we stay close enough to the global minimum as the surface becomes resolved, as local minima start popping up around us, that we don't fall off into a local minimum along the way. That we stay in. Now, this is by no means guaranteed to work. I've tried this on many models. Some of it has panned out, some of it has not yet. Is it because it's not possible? Is it because I haven't tinkered enough with all these hyperparameters? I do not know. It worked for this problem, which is how we were able to write up the paper. And I want to give you an example of what I mean now. So as beta increases, A0, the action, will continue to increase because we're cranking up the weight of this model error term. Unless we find a solution that is consistent with both the measurements and the model. Okay, if this guy suddenly plummets to 0, then the action should plummet to 0. So here are two contrasting examples so that you can understand what I mean. On the y-axis here, I'm plotting the log of the action. And on the x-axis, I'm plotting beta, that annealing parameter, starting at 0 and cranking it up to 30. Now on the left-hand side, this plot on the left, you see that as I increase beta, the action starts creeping up higher and higher until, something weird is happening with the geometry of the surface, and we plummet down to what we had determined 10 to the minus 3 is the actual global, the floor of the action, the path of least action for our problem. So this path in state space has found the true solution to the model. Over on the right, nope. We climb and climb and climb and climb and climb. We're lost. We've fallen into a local minimum. We're not going to find the solution. So you run, say, 20 or 100 of these paths in parallel searches, you don't want to dig through all of the solutions themselves. And you can. We actually did to make sure this worked. But ultimately, what you'd like to be able to do is throw away all the guys who look like this on the right and only bother to look at the guys who look like this on the left, because these are the ones that found the path of least action. So let me show you our actual result now. I'm going to show you more plots that look like that, but just first some general findings. As we expected, and again, I cannot read that because the bar is, I think it says constraints placed at the neutrino sphere only permitted a high degeneracy of solutions, as we had found a couple of years ago. But as we add successive constraints, the designs 2 through 5 that I showed you earlier, the degeneracy dissolves. And I'll remind you what those constraints were. Once the degeneracy is eliminated, we have in the plot of the action a litmus test for whether a path corresponds to the true solution. And again, that is, does it correspond to the path of least action or not? And once degeneracy is eliminated, then permitting that a sufficient number of paths is searched. You want to search enough. If you only search, I don't know, 2 or 3, well, who's to know that if you searched 100, your answer would be different. So you need to search a sufficient number of paths. Then the action versus beta plots indicate whether the true solution exists in the parameter regime you're searching. Namely, some of them find the path of least action or none do. Okay, so before I stop for questions, I want to give you visuals to go along with these words, because words are very boring and difficult to understand. Here's what I'm showing you here. The action versus beta plots. The left column is showing you the result for when we kept CM. Remember that coefficient of matter potential that governs where the MSW resonance occurs? On the left side, in the left column, it's a constant number. And on the right side, it's that quadratic form, slightly more complicated quadratic form. We obtain basically the same result for both cases. I'm just showing you both. And then the rows represent the top 4 experiments. I'm not showing you the result for experiment 5 because thankfully it was pretty trivial. But what I want to point out to you is take a look at the top left plot. So the first experiment with C constant. And I'm going to compare that with the third. So the third experiment holding C constant. What we found with the first experiment was a high degeneracy of solutions. Notice that some of the paths found a path of least action, 10 to the minus 3. When we went to actually look at the corresponding solution, though, we found that the solution did indeed obey the measurements, but not the model trajectory. That is, we had not furnished enough information to the procedure for it to realize that there was a difference between, well, I should show you this now. Let me fast forward. This is the solution corresponding to that plot that I just showed you. So the PX1, PY1, and PZ1 are the 3 polarization vectors for the first neutrino, and then P2Y, P2Z are the polarization vectors for the second neutrino. And the true is the dotted blue, so that's the true trajectory that we were challenging it to reproduce. And the red solid is the prediction of the measured state. Remember, we measured only the PZ components, and the black is the prediction for the unmeasured states.
We have a question, sorry to interrupt.
Yeah, sure.
Sanchit, you can go ahead.
Just to clarify, if you can go back on the previous slide.
Yes,
with the blue plots. Yeah, so comparing to the slide you showed earlier where you explained the annealing parameter, there was only one trajectory there. Is this plotting all 10 experiments in the same plot? Like, what are we looking at? Yeah.
Thank you. There are 20 paths represented. Thank you, I'm sorry, my fault. There are 20 paths represented on each of these individual.
Okay.
Yeah, sorry, thank you.
And the intensity
So,
is how
but
many
let me
paths?
continue. Let me continue. What I'm showing, this solution that I'm showing you here in the top left group here, this corresponds to one of the paths that found the path of least action. So what I'm trying to show you is, even though it found the path of least action, clearly we had not given it sufficient information to really pinpoint the solution, because it gets the measurements correctly at the endpoints, but there's a big gap here between its predicted location of the MSW resonance and the actual location. Sorry, there, go ahead.
Yeah. No, it was just that, and I was also curious about like the intensity shows how many of the experiments gave you a path. Is that also correct on the previous plot?
Sorry,
Sort of
one more
the
time?
intensity. So for instance, if you look at the first plot on the left, towards the bottom right, the dots keep getting darker. Is that how many paths sort of converge to that? Like what is that?
Yeah, yes. So the opacity is set. So yeah, so that you can tell, for example, most of the paths did this: up, 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 drop, because it gets darker. Darker is code for more of the paths did that.
Yeah. Okay.
Okay.
Yeah.
So I think,
Thank you.
I think we should take the rest of the questions at the end, given that we're close to the end of the hour.
Sure.
So I'll let you
Sure.
finish, and then
So-
we'll move on to the Q&A.
Sorry, I really appreciate these questions. Thank you. I timed it at 40 minutes and the wall didn't ask many questions. So I guess that's why I got away with 40 minutes. So let me contrast that with the third experimental design, which, to remind you, is up here, where we bracket the MSW resonance. We give it the value of the flavor at P's equals plus or minus 0.9. So now I want to show you the result of the solutions that, again, found that global minimum at 10 to the minus 3. That is pictured down here. Much better, much better. And in the interest of time, I'm going to keep on going and show you an example of a result where now we're searching a region of parameter space that does not contain the solution. Okay, before we were in the, sorry, I forgot to mention that. Before we were in the correct region of parameter space, now we're not. And I just want to show you a brief snapshot in, again, let's look at experiment 1 for CM constant. Some of these paths found the global minimum, but remember, they didn't have enough information to realize that they're in the wrong, they're in the wrong region. When furnished with sufficient information, none of them, it's hard to see, okay, there is a rise here. This level that you see on the, for the paths that reach the lowest value, that's not the global minimum. So check, good. None of these paths succeed in finding the global minimum once degeneracy has been eliminated from the problem. So let me end there. In anticipation of a real detected signal, we want to write the model to scale. I have been told that more than 2 neutrinos tend to emanate from a supernova event. And importantly, we want to examine the sensitivity of the procedure to contamination in real data, so a detailed noise study. And I'm at the hour limit, so I promise to never run over my limit. The audience must never suffer. So I will thank my collaborators and thank you all for listening and for your questions.
Well, thank you very much. So there's no way for the rest of them to applaud, so we have to do it over here. So there is one question in the Q&A from Bahara. So I will allow you to talk. If you'd like to unmute, you can ask your question.
Am I audible?
Yep, you're on. Go ahead.
All right. Thanks so much for the talk. I had one question. I think somewhere in the talk you mentioned that the path of the neutrino itself is chaotic and is more similar to a random walk. But we also mentioned that this technique is sort of integration blind, meaning it doesn't actually care about the path. But I also understood that we are supposed to recover this CM parameter along the path. How do we actually expect this technique to recover it if the underlying path itself is chaotic?
I'm sorry, did you say chaotic?
I thought that's what I understood, that you cannot really predict the specific path, but you
Oh.
expect the polarization vector to change over space or over the R vector.
So I did not say that the path is chaotic. It might be. We do not know. And if it is chaotic, that's a problem that we will get to if need be. But what I said was that the path of the neutrinos from the neutrino sphere to the detector is not linear, in that it's not a forward direction only trajectory. There are backscattering events. Imagine, here, can I just annotate the screen? That might be the easiest way to do this. Imagine here's our neutrino sphere and here's our detector. You can see the annotation, right?
Right, I can.
Okay, so neutrino emitted from the detector does not just, does not necessarily move in a forward direction only. Because imagine this, imagine you start off in the forward direction and then you bang into some other neutrino that's sitting here and you ricochet off that way. Okay, most of these neutrinos are never going to get into our detector. A few will, but the ones that do, they did not come in a linear fashion. They came, say, that way. Okay, so for that reason, you can't assume you know the direction of the neutrino at any particular point along your trajectory. So for that reason, forward integration is not an effective tool for studying this phenomenon, for putting it into these supernova models. And what I meant by optimization as being an integration blind technique, it doesn't care who came first, in a sense. It doesn't know, the procedure we're using doesn't know that this point is after this point. It's stupid in a sense. It's minimizing a cost function, which might end up being too simplistic. We don't know yet. Because we have not yet put backscattering in. We haven't yet tried to do that. For now, so far, we just want a consistency check that at least in within a model framework that can be solved with forward integration, we get the expected answer. Because if we don't, then we're back to square one. We can't unleash this beast on a problem that forward integration can't give us the answer to, if it doesn't already give us answers that we know are correct. Does that answer does that address what you're asking? So
It does, thank you very much.
it might indeed be chaos, and that'll be a devil of a problem to deal with. But I'm not necessarily claiming that there is.
Got it, thank you.
Okay, you're welcome, thank you.
So do we have any further questions? I know we had a lot of them during the talk, so that's great.
That's great, it's great. It's a lot more fun that way.
Well, if not, let's thank Eve again for a really interesting talk, and I will leave you with the graduate students. So everyone who's not a graduate student, you can sign off now. And thanks again for
Thank you all. Thanks so much for the
participating
invitation.
virtually. So,
Thank you.
Thank you, George. Thank you, Karen.
of course.
Thanks a lot, Eve.
Hi, thank you, Kate and Caleb. You're the only people I can see.
So Caleb is going to be in charge for the grad student part here. So once we've got...
Oh, should I stop sharing?
Whatever you guys prefer. I'm going to go, I think, just put it on mute, let you guys talk. Sometimes, you know, questions on jobs and stuff. So I'll just be kind of like getting a cup of tea, and then when you're done, I will sign on and just turn the session off. So, and I'm going to stop the recording now.
So is the
Okay.
meeting just